Okay, hi everyone. Thanks for joining our first talk in this fall of the One Word seminar. And today we are very happy to have Denny Wu here to give us a talk on his recent work on feature learning. So Denny is currently a PhD student in computer science at the University of Toronto and Vector Institute under the supervision of Jim Barr and Murat Erdoğdu. And before that, he was a undergraduate student from the CMU, and his recent research focus is in deep learning theory and over parameterized networks. And thanks for joining us, and let's enjoy Danny's talk.
All right. Thanks for having me, and I'm very happy to be able to participate in this seminar. Okay, so let me share my screen first. So I am sharing my screen, right?
Yes.
Okay, awesome. So I'd like to tell you about some recent theoretical results on feature learning in two-layer neural network. This is joint work with Jimmy and Murat at the University of Toronto, Taiji at the University of Tokyo, Zhichao at UCSD, and Greg at Microsoft Research. So a preliminary version of this work is currently in submission. It was submitted to some conference that shan't be named, but the results will be out probably later today. I'll be talking about some basically an extended version where we have a few more results. Hopefully, this will be on archive. The archive version will be updated soon. Okay, and please stop me anytime you have questions or remarks. Right. So okay. The model that we study is a two-layer neural network with capital N neurons. So the input data X is a d-dimensional vector. And for each neuron, we're going to take the inner product between X and the ith neuron. So the WI, this is also a vector in RD. And then we're going to apply an element-wise nonlinearity. And then it's going to be multiplied with second layer AI. Okay, so we can also write this in a more concise way. So now this sigma nonlinearity is going to apply element-wise to the vector. Okay, so now my weight matrix will be of size d times capital N, and the second layer is going to be a capital N dimensional vector. So, oh, and by the way, we omitted the bias unit here for simplicity. So this model is usually learned via gradient descent. So given that the loss is convex, which is usually the case, if we fix the first layer and only optimize the second layer, well, this is a linear model on top of your features, and this is going to be a convex problem. In fact, if you use a squared loss, that is a closed form solution to it. But if you want to optimize the first layer, then even if the second layer A is fixed, then this problem is still often non-convex. Okay? And so this is usually more challenging. So our goal is to say something precise about the performance of this learned model, learned via gradient descent, in some procedure that I'll mention later. So training-wise, we're just going to do empirical risk minimization using the squared loss, the MSE loss. So we're going to be given n training data, and the training label is going to come from some target function or the teacher model f star, and also potentially corrupted by some label noise. So for training-wise, we're just going to evaluate this objective over n training points. And at test time, we're going to compute the prediction risk, or I'm going to use this interchangeably with a generalization error or a test loss. They're roughly equivalent. So now I'm going to compute the squared loss, but now under the expectation. And this is the expectation is taken over the same distribution where the training data is drawn from. Okay. This is also the L2 norm of the difference between these two functions. So, okay. And the regime that we'll be interested in is the proportional asymptotic limit. So what that means is that the number of training points n, the size of the input, so the number of input features d, and the width of the neural network, capital N, they all diverge. But then the ratio between n and d, between all these three quantities are going to stay fixed, and they're going to be like constant. So now under this parameterization, increasing the size of your sample corresponds to having a larger psi1. Okay? And increasing the width of the model or over parameterizing is going to correspond to having a larger sign too. So I'll be using these two terms to will designate sample complexity, the sample size, and the over parameterization. Okay, so why do we want to analyze this regime? Well, one thing is that the scaling kind of tells you that the size of your model is comparable to the number of training data, which is you can argue this is reasonable. So we don't really assume that the width is very large compared to everything else. But more importantly, in this limit, if we make strong assumptions on the input data, which we will, it's actually possible to say something very precise about the prediction risk. Okay. So here are the prior results on this precise asymptotics. So recall that. So we have two sets of parameters. We have W and A. And if we fix the first layer and we only train the second layer, then we essentially arrive at a kernel model. And so the features are defined by the so-called hidden representation of the neural network. So basically the activations patterns after the first layer. And we're going to refer to this kernel as a conjugate kernel, or the CK. Okay, so if we do kernel regression on the CK, that basically means fixing W and learning the second layer. And there's also a different kernel called the neural tangent kernel, which is associated with the derivatives of the parameters at initialization. So this is we're not going to spend too much time on this kernel, but this arises from gradient descent on certain wide neural networks. So so these W are always randomly initialized before we train them. But if we fix them at initialization, then these models are referred to as random feature models. And for random feature models, then we can compute the exact prediction risk in the mentioned proportional asymptotic. So there's been plenty of prior works on this. And if you've seen this kind of good-looking figure in the context of double descent, a lot of them were studying this random feature model in the proportional asymptotic. Okay. So now the question is, well, okay, so we have two sets of parameters, and if we're training the second layer while fixing the first layer, then we can get the precise performance. This has been done already. So you may ask, well, does this training half of neural network already gives you some evidence of for example, the efficiency of this two-layer model in learning some target function? And I would say not quite. And the reason is that in high dimensions, actually, these random feature models can only learn a very limited class of functions. So what I mean is the following. So consider the random feature rich estimator. So we're doing rich regression on these the random features that are either the conjugate kernel, so second layer, so fix the first layer, train the second layer, or the neural tangent kernel. And we can tune lambda to be anything. So you can pick your best lambda. And the prediction risk of this random feature model on either of these features is going to be lower bounded by this quantity. Okay, so what is this? So what is this quantity? So this is a projection operator. So if you give me a target function f star in L2, I can decompose it into the constant part, that's the expectation, and the linear part and the quadratic part, etc. So this is almost like a Taylor expansion, but under the specific input distribution. And this p greater than 1 means that I'm going to remove the constant part and the linear part of my target function, but I'm going to keep everything else here. And the lower bound on the prediction risk is just going to be the L2 norm of whatever is left. So basically anything that's not linear in your target function. Okay, so what this tells you is that, well, in the proportional limit, these random feature models can only learn linear functions. Okay, because everything else, like starting from the quadratic part, the prediction risk is lower bounded by the L2 number. So you can't learn anything. So of course, you might if you employ a naive parameter counting argument, you can be like, okay, a degree k polynomial probably needs d to the k samples to be estimated. So this is kind of like a natural barrier because we're in the proportional limit. But the point is, for learning certain class of functions, for example, if the target function is sparse or it has certain low dimensional structure, we would expect neural network to be able to learn something nonlinear, even if even when the input is high dimensional and it concentrates in certain ways. Okay. So now you can ask, like, where does this gap come from? Well, there are many explanations, of course. For example, this kind of lower bound usually requires the input to be like isotropic, or it basically looks like a Gaussian or sphere. But real world data doesn't look like that. So perhaps there are already low dimensional structure in real world data. So if we do theory on Gaussian, the isotropic Gaussian doesn't make too much sense. But our perspective is that we want to incorporate the learning of the first layer, because this is usually what happens. So in other words, we actually, the features of this neural network is actually trained also via gradient descent. Okay. So in particular, if we optimize the first layer, then we expect the neural network to kind of adapt to the learning problem. And hopefully the representation is going to be useful, so we can reduce the sample complexity. But of course, in random feature model, you fix the first layer so you don't learn representations. The same for the NTK model. So our goal is to, since we're already in the proportional asymptotic limit, so we want to do precise asymptotics. But now, instead of doing it on the random feature model, we want to first learn the features in some ways. And then particularly, we want to learn the first layer via gradient descent. But this is a hard problem in general. So we have to restrict the scope a little bit. So we're going to focus on only the beginning of training, and this is partly motivated by some empirical observations that the non-kernel behavior of neural network usually occurs in the beginning of training, in the first few epochs. But mostly this is because this is if we restrict ourselves to the early phase, then we can still do the precise asymptotics. We can still do some computations. So basically, our perspective is to do the precise analysis for the learned kernel, and we're only going to be looking at the conjugate kernel. So we're going to learn the first layer, and then we're going to learn the kernel on top of the first layer representation. And the first layer is going to be learned by taking a few gradient steps. Okay, I'll specify how many steps we can take afterwards. Okay, so any questions so far? So that's so much for the motivation. Now we're going to move into the problem setting. I guess that means no questions. All right. So again, I want to remind you the proportional limit here. So basically, increasing the sample size corresponds to larger psi 1, and increasing the model width corresponds to larger psi 2. Okay, and we're going to assume that the input is just isotropic Gaussian, and we're going to and there's going to be a target function, or the teacher model, and it's going to be Lipschitz, and there's also going to be some IID label noise here. And we're going to center the activation. This is just for some technical reasons. So we're going to assume the expectation of the activation under this Gaussian is going to be 0. So this is satisfied, for example, for like 10H, pretty much only like or error function, and or you can center a ReLU by subtracting the mean. We're also going to require the this quantity, which is kind of the expectation of the derivative, to be non-zero. So roughly speaking, this means that the activation is like, this is satisfied for most of the activations that are monotone, of course, but this is kind of saying that the activation has a linear component. And we're going to initialize the parameters to be Gaussian, both the first and the second layer. And if you remember the definition of a neural network in the beginning, we actually have a 1/root capital N prefactor already. So that means that now if we initialize the second layer to also have variance 1/n, the second layer coefficient actually scales with roughly 1/n instead of 1/root. Okay, so this means that we're actually in the so-called mean field parameterization. So the second layer, if you include this prefactor, is actually going to be very small. And the reason we do that is now, if under this scaling, the weights do not freeze around initialization, even if the size of the model becomes large. Okay, so so here's a simple demonstration of this in 2 dimensions. So the data is high dimensional, but I'm just picking two dimensions to visualize. So if you drop this 1/root n prefactor, that gives you basically the NTK parameterization. Now, if you run gradient descent on this the problem, like each of the neurons don't travel too much. So here I'm plotting the trajectory. So this dark color is initialized parameter, and after they train till the training loss is small is the yellow dots. So they don't move too much, but the loss already becomes low. But if you add this prefactor, now each of the neurons have to move quite a bit. And the target is the teacher model has 2 neurons. So now, so you can actually recover the direction of the target. Okay. So here's our training procedure. So remember, we're trying to learn the feature, so we're going to do gradient descent on the first layer. So the objective is empirical MSE loss, and we'll be taking t steps. And this is just the expression of the gradient, which we'll revisit in a bit. And by early phase, I mean that the number of gradient steps that we take is going to be fixed as the rest, like the size of the model and your input, like the number of training data goes to infinity. Okay, and actually in some cases we're only going to be looking at the first step. Okay, so this is so we do not allow t to scale with like n and d. So meaning that t should be you should consider t to be small compared to the other quantities. That's why this is like early phase 100%. Okay. So and after we learn the features using for like t gradient step, we're going to evaluate the quality of the representation by just running ridge regression on the on this learned representation. And one caveat here is that after we learn the parameters, like the first layer W, like this parameter is not going to be independent of my training data anymore, because I'm training on this X. So now when I evaluate the kernel, this is like I don't have this independence, which makes things rather messy. So instead, we're going to cheat a little bit. Where when we learn the kernel, when we do the kernel ridge regression, we're actually going to use a fresh set of data, which for simplicity we're going to assume it has the same size as the original data set we used for feature learning. Okay. So and then so this is a ridge regression objective, and we're going to denote the prediction risk of this kernel model on the trained features as RGD. Okay. And so our goal is to compute this the prediction risk of this trained kernel, and then we're going to try to show that this is going to do better than the initial random feature, and potentially this lower bound. That's just basically saying that random feature models are linear in high dimensions. So one of the annoying things here is that, well, like a priori, I don't really know what's going to happen to my trained weights. So, but it's of course I cannot assume that after training my weights are still like IID Gaussian. So then it's not clear what kind of theoretical tools we can use to get the precise asymptotics out of this. And here's the point that here's where we're going to use the early phase assumption to simplify things considerably. So by early phase, I mean that now my weights. So let's define this constraint set. So this is basically a constraint set that's telling you that my weights W is close to my initialization. So this initialization is Gaussian from previous slides, measured in these 3 norms. And for simplicity, we're going to take the speed to be a constant, although it can actually depend on D in a certain way. Okay, so if my W fall into this constraint set, that means, well, I haven't really moved too much. Okay, so okay, and before I tell you about the gradient, the structure of the gradient, so just I'm going to remind you where these coefficients come from. So we can do an orthogonal decomposition of the activation function. So my activation function, this is a function from R to R. I could decompose it into a linear term and something that's and the remaining like nonlinear part. Okay, and the coefficient for this linear term is just going to be the expectation of the derivative, or you can also write this as z times sigma z. And what this is orthogonal decomposition in the sense that the expectation of the orthogonal part and also the expectation of z times the orthogonal part are both going to be 0. Okay, so just to remind you that, so now this mu1, this kind of tells you how big of a linear part my activation function has. Okay, so the observation here is that so when my weights belong to this constraint set, then its gradient can actually be approximated in operator norm by some rank 1 matrix. Okay. So in particular, what I mean is that, so we can define this rank 1 matrix A, which is x y a transpose. So so y is my label vector, a is my second layer, so this is rank 1. So now if I look at, and the coefficient is going to be given by this like the strength of the linear part of the activation function. And so if I look at the difference between the actual gradient evaluated on this W and this rank 1 matrix, this is going to be much smaller than the norm, operator norm of the gradient itself. And in fact, it's going to be roughly root capital N times smaller. Okay, so this means that, well, if you only care about the operator norm, then this is a pretty good approximation. Okay, so you can, but of course, it's a priori. We also don't know why operator norm is sufficient, right? So because in this neural network, there's going to be a nonlinearity that's applied element-wise. And so it's not clear why getting an operator norm approximation of the gradient is going to be sufficient for you to ignore the rest of the parts. And just a side remark is that this rank 1 matrix is not like a useless like random matrix. This actually contains information of the target function or the teacher model through the training labels. Okay. Okay, so just to give you some quick intuition, so this is actually a very intuitive observation. It comes from the fact that most of the activations that we use are like monotone, so like whether they're non-increasing or non-decreasing. Okay, so in this case, if you look at the derivative of the activation, it's just not going to be centered at 0. It's going to be like all positive. So now, if you write down so if you remember the definition of the gradient, there's going to be a Hadamard product with this derivative matrix. And because the derivative matrix is not centered, you can separate out like a 1-1 transpose, and then the rest of the matrix is centered. So now this 1-1 transpose, this uncentered part is going to give you a large rank 1 spike. Okay, and then the remaining part is going to give you the remaining part that's full rank. This is going to be the residual. And it's going to be easy to see that these two parts, this rank 1 part and the remaining part, they're going to have roughly the same Frobenius norm. So if you look at each entry of the two matrices, they're going to have roughly the same magnitude. But then because this matrix is rank 1, so the operator norm is going to be much larger. So that's why if you only care about operator norm, you can actually ignore this residual matrix. Okay. So and of course we need to answer the question of well, when do my parameters fall into this constraint set, right? So obviously at initialization, I'm good. So because at initialization, my weights are exactly my W0. So for the first gradient step, this rank 1 property definitely holds. So what we can show is that if your learning rate is theta 1, so if your learning rate does not grow with the dimensionality, and you take any finitely many gradient step, so the number of steps you take also cannot grow as n go to infinity, then your weights after t gradient steps is going to fall into this constraint set with high probability. So the interpretation here is that, so this is basically saying that if this is the linear rate that I'm using, then after t, for the first like t gradient steps, my gradient matrix is going to be approximately rank 1 if you look at the operator. Okay. So the consequence of this is that we can simply sort of accumulate the rank 1 component. We can accumulate this rank 1 matrix A, and this tells us that if I run gradient descent with for t steps using learning rate eta I that's of constant order, this is roughly equivalent to running gradient descent for 1 step, with learning rate being the sum of eta i's. Okay, this just come from accumulating the rank 1 matrix for t steps, and so we'll be using this equivalence quite often. Okay, and of course, this eta equals theta 1. This is not the only like meaningful learning rate, right? So it's not clear that there's definitely other choices of learning rate that are that can also give us interesting phenomena. So so now we're going to zoom into the first gradient step, and we're going to try to see like what are the reasonable learning rates we can choose for this early phase of training. So the previous learning rate that I mentioned in the lemma, this constant learning rate, what it's telling you is that you're essentially matching the operator norm of the update with that of the initial weights. Okay, so remember W0, this is initialized from a Gaussian. So each entry has variance 1 over d. So the operator norm here, operator 2 norm here is going to be roughly of constant order. So this is saying that the change after 1 gradient step, an operator norm is also going to be of constant order. Okay, so this is the, and we call this a small learning rate because now you can ask, well, what if we match the Fabenius norm? So because the gradient is almost rank 1, now if you match the Fabenius norm, you have to take a much larger step. In fact, the learning rate needs to be root capital N here, so that the Fabenius norm of the update is roughly the same as the Fabenius norm of the initial weights. Okay, so these will be the two learning rates that we'll be interested in, so that we'll analyze in and so how to interpret these two choices? Well, the small learning rate, this constant learning rate, kind of reminds you of the neural tangent kernel kind of setting, in the sense that if I take one gradient step with this learning rate, my weights have moved, but they haven't moved too much. So the change in each of the parameter is going to be much less than the initialized magnitude. Okay, so that's why it's this is kind of at high level, this resembles the kernel regime. Okay, but so the weights haven't moved too much, but it turns out that they've also moved sufficiently far enough such that there's actually not something non-trivial going on in terms of feature learning. So in fact, this is actually the smallest learning rate at which something non-trivial happens, because you can also show that if the learning rate is smaller, sorry about the alarm. You can also easily see that if the learning rate is smaller than constant order, then after one step or any finitely many steps, your kernel don't change. So if you run ridge regression, the prediction is going to be the same. Okay, and so this is a regime where like the weights have changed a little bit, but then the kernel, the prediction risk of the kernel has already has a non-trivial change. But because of this closeness to initialization, we can still do the precise asymptotics. This will be in the next few slides. And now this very large learning rate, this eta equals root, and this mirrors the maximum update parameterization from a recent paper. So this is a parameterization that really pushes the features or the weights away from initialization, in the sense that after one gradient step, each feature is going to change roughly constant amount, which is also the same. This is roughly the same as the magnitude that they're initialized from. Okay. So after this, if you use this large learning rate, then after one step, you're completely you're out of the kernel regime for sure. And to some extent, this is going to be the largest possible learning rate that we can use, because if you use a learning rate that's larger than this, then the pre-activation feature after one gradient step is going to blow up asymptotically. Okay, so these will be the two learning rates that we're looking at. I think I should pause for questions. Or
Oh yeah, Danny. I just have a very small question. Actually, it's on the 12th. Yeah.
12?
I think it's a little bit previous. Yeah, it's about the accumulation of the gradients with smaller. Yeah. My question is that is this rank 1 matrix A always the same? If that is the same,
yes.
then I can I assume that the accumulation is always following the same eigenvector direction of this rank 1 matrix?
It is. So this rank 1 matrix is fixed. It does not depend on T. So this is always the same. So you see, like this is we're using the same data, and I'm only training the first layer. So A is also fixed. Yeah. So you're at each step you're following the exact same direction.
Okay. Then am I correctly interpreted this phenomena that if I always accumulate this rank 1 matrix, then this might be some limitation from this small learning rate regime, that I can only learn part of the information from the data?
Exactly. Yes. So in fact, you can only learn like you basically in this small linear rate regime, like doing gradient update is kind of just like doing rank 1 perturbation on your weights. So you can't learn. For example, if my target function occupies more than one direction, yeah, you can't learn in this phase. Yeah. So you're right.
Okay. Okay.
So
Thank you
if you
very
look
much.
at yeah. So I'm sorry, I have to go back a bit. So this is kind of, so if you look at this figure, like my target function has like two directions. But in the beginning of training, my weights are actually going to move, like all the weights are actually going to move in this direction. Like this is one direction. So this is like the early phase. And then they're going afterwards that they can like adapt to different directions. But because we zoom into this like early phase, now the gradient is rank 1 and operator. So
okay, so in your plot, the learning rate is a 1 or
you can think of this as a small linear rate plot, but this is not the early phase. This is training all the way to convergence. So
So basically, you see, you can observe that in very early steps, they all trend in the one direction, but only in the
Exactly, and you
later.
can see this, yeah, both in this figure and this figure, right? So you can see that they all move like in this direction.
Okay.
And this direction is happen to be the linear combination of these two directions. So
okay, thanks.
Yep. All right, thanks for the question. Okay, so so let's look at the small linear rate first, because that's where we can say a lot of precise things. So yeah, so like the question already alluded to this. So in the small linear rate regime, like doing gradient descent on the first layer is kind of just like doing a rank point perturbation. So then we naturally expect a spike model of the weights after you train for like t steps, as long as the sum of the linear rate remains bounded. Okay, so here I'm plotting the eigenvalue distribution of the weight matrix, or okay, the singular value distribution, or you can take the transpose. So here you can see that most of the eigenvalues actually don't change. So this, because I initialize the weights from Gaussian, for W0, this is going to follow like a Marchenko-Pasteur. This is going to have a Marchenko-Pasteur spectrum. But then we're going to see one outlier. It's going to be one isolated singular value. And so, okay, so the bulk doesn't change. But then this outlier, if you look at the direction of this isolated singular value, it's actually going to align with my beta star, which is the linear component of the target function. Okay, so here in the experiment, I'm taking the target function or the teacher model to be one neuron. So and the neuron points towards this beta star direction, and it's half of it is -1, the other half is like +1. So now you can see that it's if you plot the singular vector, it's actually roughly following this the direction of the teacher vector. Okay. So we can actually say something very precise about the spike model. So for that, we first need to, so remember we previously did an orthogonal decomposition of the activation function. So now we're going to do this for the teacher model. Okay, so we can decompose the teacher model into like a constant part, a linear part, and the rest we're going to clump, like just group them together. And now this mu1 star is going to give you the strengths of the linear part of the teacher model, just like mu1 tells you how big of a linear component you have for the student nonlinearity. Okay, and the norm of the nonlinear part is going to be mu2 star. So this is the theorem is basically a BBP phase transition in the leading singular vector of the weight matrix after t gradient step, where the sum of the linear rate is designated as eta. So basically, I'm not going to go through the formula, but essentially the message here is that when eta exceeds some threshold, then we're going to expect a spike. So there's going to be an isolated singular vector, singular value. And if we increase the linear rate, the spike is going to become larger. Okay. And if we increase the sample size, this spike is going to have better alignment with the teacher model with this vector beta star. Okay, so this is a magnitude of the singular value, and this is how much the corresponding singular vector aligns with this target direction beta star. Okay, so naturally, so now based on this, you would think that okay, so after training my weights, at least in this regime, that like most of the things don't change, but then there's going to be a spike, and the spike actually contains information of the linear component of the target function. So this should help, like this should be beneficial in terms of learning certain target functions. Okay, so we're going to try to like rigorously show that this is the case by computing the prediction risk of the kernel ridge regression estimator. Okay, so we also have a conjecture for, so it turns out that after one gradient step or multiple gradient step, if your linear rate is not too large, then you're also going to see one spike in the conjugate kernel. But we did not. I think for the interest of time, I'm going to skip this part because it's actually this part is not needed for the risk computation. But it's just I think the interesting observation here is that after one gradient step, you can actually see that the leading eigenvector of the conjugate kernel matrix is going to start to align with your training labels. So this is the kind of evidence that your kernel is like adapting to the data to your training data. Okay, so now let's look at the prediction risk. So because we've seen that, well, after the first gradient step, we're probably going to see a spike, and the spike is going to align with the linear part component of the teacher model. So now we're going to compute the prediction risk, and we're going to restrict ourselves to a teacher model or target function that's just one neuron. This is also referred to as a single index model. Okay, so this is a setting that there are multiple reasons that we're setting this setting. One of it is just is that we only have like one spike after in the beginning of training, so we're probably not going to be able to learn like multiple directions in this phase. But the other is that actually, in terms of the precise asymptotics of random feature model, there's actually multiple works that uses this single index target function as like a canonical example. So just to remind you, we want to compute the prediction risk after the first layer weights are trained for key steps. And then we do ridge regression on top. And so we're going to look at two different learning rate scalings. So there's going to be a small learning rate. And this is the regime where we can do precise asymptotics, and we can show that the trained kernel always improve upon the initial kernel. So here, the yellow line, these are the prediction risk of the initial random feature kernel. And this pink, red, wine red, this color, this is the what happened if you train your kernel using the small learning rate and then do the ridge regression. So this always improves upon this the initial random feature, but it's not going to improve too much in the sense that here you're still staying in the linear regime, so you cannot beat this like lower bound. Okay. And to beat the lower bound, you need a very large learning rate. And here we show that if your f star is special, by special I mean it basically has to be like a 10H or an error function, then if you do one gradient step with this learning rate, you can actually achieve almost vanishing prediction risk, and that's way better than just like linear lower bound. Okay, so that's going to be the rest of the talk. Okay, so let's look at the small learning rate first. So for this setting, we are going to use the Gaussian equivalence property to derive the precise asymptotics. So so to do that, so I'm going to define the prediction risk of for two different random features. So first, so this f refers to, can either be ck, which is my original nonlinear random feature, or GE. It refers to this indicates Gaussian equivalence. Okay, so so this this Gaussian feature, you can see there's no nonlinearity here. Okay, so I'm essentially the intuition here is that remember we can write the sigma in this orthogonal decomposition. So so then we can decompose this into like mu1 times wx plus like remaining terms, like the remaining higher order terms. And here for this Gaussian linear feature, all we're saying is that, well, we're going to keep this linear part, okay, and for all the high order parts, we're going to replace it with Gaussian with the same variance. Okay, so this is a way to essentially linearize your feature map. So now the nonlinearity is gone, but if you compute the first two moments of these two feature maps, they're going to be the same roughly. Okay, and so now I have the prediction risk of my random feature rich estimator on these two different features. Okay, and a priori you might think that like, why would they be the same? This is like a nonlinear feature map, and this is linear. Like so, like, they can't be like these two can't really give you the same prediction risk. But the Gaussian equivalence property is saying that the prediction risk of the rich estimator on these two different feature maps are going to be roughly the same. Okay, and I'll give some intuitions in following slides, but I should note that in all the previous works, this property has been shown for random feature model. So if you do not train the weights, then when your input is Gaussian or sphere, and if your weights are random, then the prediction risks of these two different models are indeed asymptotically the same. Okay, but we have to extend this to train the features. Okay, so what are the implications? Well, the good thing is, with this Gaussian equivalence property, now we don't have to worry about the nonlinearity anymore. We can compute the prediction risk of this linear model, and everything here is like Gaussian. Like W is Gaussian, Z is Gaussian, and this X is Gaussian, Z is Gaussian. W is like Gaussian plus some low rank thing. And this is not hard to do. But the bad thing is, because of this equivalence, then so this equivalence telling you that your nonlinear random feature, your nonlinear kernel model have the same prediction risk as some Gaussian linear model. So of course, you cannot learn anything nonlinear here. So essentially, this Gaussian equivalence property also entails a limitation of your kernel. Okay, it's basically, as long as this property holds, then the prediction risk of your kernel, no matter if it's random or trained, is never going to beat this line. Okay, because this is the best. This is a line that that indicates the best performance of performance of the best linear estimator on the input. But because of but if this equivalence holds, then your risk is the same as that of a linear model. So you can't beat that dash line, which is a bit underwhelming. This is saying that you're actually better off just directly training like linear regression on the input. Okay. But we can still do precise asymptotics. So here this is a theorem that tells you that if we do the small linear rate setting, so I can take I can train my parameters for t steps, but t does not grow with n and d, and the sum of linear rate has to be also a constant. Then if you do ridge regression on the train feature map after t gradient steps, the Gaussian equivalence property is going to hold. Okay. So, and the intuition is that previously, like there's already been works proving that the Gaussian equivalence holds for the random feature. So now we're just doing like a small perturbation analysis to show that this also holds when your weights are not too far away from the random initialization. So then this property is so because your weights are not very far away from the initial Gaussian, this property also holds. Okay. So just to illustrate the power of this Gaussian equivalence, so now we can actually compute the asymptotic prediction risk of this for the trained kernel, and so now the dots here are the empirical values. So here I'm training for more gradients. Like the x-axis is how many gradient steps I'm training the model, and the y-axis is the prediction risk. And these solid lines are the asymptotic predictions using Gaussian equivalence. Okay, and you see they're a very good match. So the message here is that, well, if the learning rate is not too large, then we're going to expect the Gaussian equivalence to hold in the early phase of training. This is early phase because t has to be fixed while the rest of the things diverge. Okay. Just from the figure, you can see that the prediction risk is going to improve upon so because when t equals 0, that's your initial random feature. So your prediction risk is going to improve, but then it's still going to be lower bounded by this line. That's just because of the Gaussian equivalent. So you cannot, as long as your model has the same risk as a Gaussian linear model, you can't be below this line. Okay. So we're going to say something more precise about this improvement. So now that we have the Gaussian equivalence model, so we want to get some asymptotic formulas for the prediction risk, and we want to rigorously show that you can outperform the initial random feature model, even though you cannot. You're still going to have the lower bound because your model is linear. Okay, so this theorem essentially tells you that, well, if your learning rate is of constant order, then the difference between the prediction risk, so of the initial random feature model, so this is R0, and the one with the trained kernel, this is RGD, is going to converge in probability to some function that depends on these parameters. Okay. We're going to take a closer look at this function delta in the next few slides. But so essentially, this formula and this R0 has been computed in many previous works, because, as I previously mentioned, there's a lot of works that already studied the asymptotics of the random feature model. So because we have the asymptotics of this difference, we can also plot the prediction risk for this trained kernel. So these are just figures that tells you that we the empirical value, these dots, and the prediction that's given by this formula are aligned when the sample size is like 10 to the 3 to 10 to the 4. Okay, but I'm not going to show you exactly the formula of delta, because it's actually, it looks a bit messy. Okay. So with this formula, now we can try to say something about whether feature learning is going to improve your representation. Okay. So here are a few basic properties of this function delta. The first one, and probably the most important one, is that this is a non-negative function. Okay. So remember, this is the difference between the initial your random feature risk and the risk of the trained kernel. So if delta is positive, that means training improve the prediction risk, which is what we want to see. So the first thing is this function is non-negative for any choice of these hyperparameters, as long as they're not diverging. And moreover, this function is going to vanish if and only if one of these quantities is 0. So what are these? So mu1, this is a linear component of the student model. So this is almost always true because the activation we use are like monotone. And this mu1 star is a linear component of the teacher model, because this is a part that we can learn in a small linear regime. And if eta is 0, then like we're not doing anything. Okay, so the message is that for if this is if your learning rate is at this order, then future learning always improves upon when these conditions are satisfied. Future learning always improves the representation, in the sense that the prediction risk of the kernel estimator is going to be lower than that of the initial random feature model. Okay, so this is what you so here this is, you can see it from this figure. So this darker color corresponds to the initial random feature, and as you increase the learning rate, your prediction is going to become better. And moreover, as you can also see from this figure, this delta is actually an increasing function with respect to the learning rate. Okay, so if you take a larger learning rate from 0 all the way to infinity, your prediction risk is going to strictly decrease. So you're going to do better. So if you take, so remember this this learning rate eta can also be interpreted as the sum of the learning rates over t steps. So this means that if you take more feature learning steps, and if you take larger step size, then the improvement is going to be you're going to get more improvement. Okay, as long as you're still in this initial phase, like this eta remains to be like theta 1. Okay, so this is actually a provable improvement over the initial random feature model. Okay, so you're always going to do better, and if you take more steps, you're going to the risk is going to further decrease. This can be seen from the figure. And a side remark is that for this to hold, we don't really need the student and teacher to have the same nonlinearity, because again, in this regime, we're learning the linear part of the linear component. So now you can so we can also look at a few special cases. For example, here what you can see is that when the learning rate becomes large, then your prediction risk might actually approach this lower bound. Okay, and this we can actually rigorously show. So if we take the linear rate eta to go to infinity, but note that this limit is taken after the nd and capital N and to infinity limit. Okay, then the prediction risk is actually going to match the lower bound up to some factor that becomes small when psi1, which is sample size, becomes large. And this holds true for any width of the model. Okay, so pictorially, what this is suggesting is that, so we can look at the figure on the right. So this here, the learning rate is large, so the learning rate is infinity. So now if you increase the sample size as psi1, then the prediction risk of the trained kernel is going to approach this lower bound. So it's basically going to completely recover the linear component of the target function. Okay. So why is this an interesting result? Because if you look at the initial random feature model, so this is without training the representation, then even if you let the sample size go to infinity, there's still going to be a gap. Okay, so even when psi1 is large, the prediction risk is not going to reach this dashed line. Okay, so and in fact, we know from prior works that in order to like close this gap, the width of the random feature model needs to be very large. Okay, so actually the width needs to tend to infinity for you to exactly match this line. So therefore, the message here is that, well, if you train your kernel, then even if then you can match the performance of a very wide random feature. So this is kind of like so feature learning kind of saves you a bit of width. Okay, so to achieve previously for random feature to achieve this lower bound, you need like a very wide model. But now, if you take like one step or multiple steps with sufficiently large learning rate, then this holds for any width. So for any width, you're also going to reach the same lower bound. Okay. So this is one special case that we can consider. And the other limit that we're going to look at is when the width goes to infinity first. So this is psi1, psi2, like the width of the network divided by the input dimensionality. When this diverges, then delta actually go to 0. And this is not surprising because, as I previously alluded to, so when the width of the random feature model goes to infinity, you can already sort of match this lower bound. So in this case, because under the Gaussian equivalence, the trained model also have the same lower bound, so it cannot beat this dashed black line. So therefore the improvement is going to become like less significant. So here what I'm plotting is the heat map of the prediction risk. So on the left side, this is the initial random feature, and since lambda is small, I think here lambda is like 10 to the minus 3. You're going to see a diagonal line here. This is the double descent peak. Okay. And on the right side we have the improvement. Okay, so this function delta, and it's also going to have this diagonal line because it's when the risk is large, then there's also like more room for improvement. But if you ignore this, then what you can see is that the benefit of feature learning is going to become more prominent when the sample size, psi1, is large, and also when the width is not too large. So it's going to be in this regime, because when the width is large, then the prediction risk is already small, even for the initial model. So this is so essentially this feature learning is both beneficial for a large sample size and also not so large model. Okay. Okay. I think I'll pause for question, and then I'll have like 2 more slides. All right. Okay. I guess that okay. I'll just continue. So if you remember, so from this analysis of the small learning rate, what we can see is that, well, if you take a larger step, or if you take more steps, you're going to get the prediction risk is going to become better. That's so that's what's shown in this figure and also in this theorem. So now the natural thing to ask is, well, can we further increase the learning rate, right? Because but by that I mean now this learning rate eta has to grow with n and d, because otherwise if we let eta to be fixed while everything else diverges, then that's already covered by the previous case. Okay. So we're going to look at one very simple case of this large learning rate setting. We're going to take only one gradient step, but the learning rate is very large. So this is, if you remember, this is the largest learning rate that you can possibly take. Okay. Otherwise, the pre-activation features are going to diverge asymptotically. So one gradient step with this root capital N learning rate, and so we're going to see what happens in this regime. So the good thing is that, well, now your weights are very far away from initialization, because this learning rate is very large. So previously we've shown that if your weights are close to initialization, then we expect the Gaussian equivalence property to hold. And if the Gaussian equivalence holds, then your random feature model is roughly the same as a linear model. Okay. But now, because my weights are very far away, so we will expect this Gaussian equivalence not to hold. So I can potentially learn something nonlinear. Okay. So that's a good thing. But then without the Gaussian equivalence, so this GET is a Gaussian equivalence theorem, I don't really know how to do the precise asymptotics. Okay, so here we're going to cheat a little bit. We're going to just alternatively upper bound the prediction risk of the ridge regression estimator after the features are trained with this large learning rate. And we're going to hope that this upper bound is already tight enough that we can beat the lower bound. The kernel lower bound is going to be that dash back black line. Okay. Because we don't have the precise asymptotics, the analysis here is actually follows mostly from the non-parametric, like the kernel ridge regression literature. So what we do is that we first show that after you take one, because remember the target function is just a single index model. So what we can show is that after you take one large gradient step, we can actually construct some second layer that achieve low prediction risk. And also the norm of the second layer is not too large. And if we can show that, then ridge regression is also going to be good, because like the ridge regression objective is basically the argmin of your loss and the L2 norm. So this is based on construction. So we basically were able to show that there exists some subset of neurons after one gradient step that gives you reasonably low prediction risk. Okay. And this construction is based on this constant tau star. So this tau star kind of tells you how how good your feature is in some sense. So this is if you want to interpret this formula, this is this sigma star. You can think of this as your teacher model, and the sigma, this expectation over sigma, this is kind of like a idealized version of your student model. So this tau star is like it kind of serves as some kind of bound on the prediction risks that ridge regression can achieve. Okay. So we first show that there exists some second layer coefficient that achieves prediction risk that's pretty close to tau star. And after that, we can show that if we do ridge regression, and actually the lambda here can take a very wide range of values, then the prediction risk is going to be 10 times tau star. And this constant 10 is not optimized. So essentially, so now the question becomes, well, when when is this tau star small? Okay, because when tau star, this constant, is much lower than this lower bound, then even if you multiply by 10, it's not going to be a big issue. We're still going to the learned kernel is still going to outperform this kernel lower bound. Like that's basically the best of the best that a linear estimator can do. So here we have two examples. So if you have if both the student and teacher are 10H, then the prediction risk, I think this tau star is like 10 to the minus 4. So then if you take one gradient step, then you can already beat this kernel lower bound. And what's even better is if you take these two to be error function, then tau star is 0. So now, based on this upper bound, you can see that the prediction risk is going to have roughly a d over n rate. Because so tau star here is 0, so the only remaining term here is going to be psi1 minus 1. So this is just the d over n. And this is essentially so even though this is an upper bound that might not be tight, but we can also see this d over n rate when we actually run simulations. So what this is saying is that like if your tau and tau star, if your sigma and sigma star satisfy certain conditions, because this tau star is a one-dimensional Gaussian integral you can evaluate numerically, then after one gradient step, you're going to outperform all the possible random feature models or rotation varying kernel models in high dimensions. But I should note that, like again, this tau star depends on these two nonlinearities. So we do not claim that for any choice of student and teacher like model, one gradient step is sufficient to actually beat, for example, beat this kernel lower bound. This is not true. For example, if you take one sigma to be like ReLU and this to be sigma star to be 10H, then this tau star is going to be like 0.1 or something. And then if you multiply it by 10, this is quite vacuous. So because again, our goal is not to show that after one gradient step we can learn like an impressive class of single index model. We're just trying to see what's we're just trying to see if there's some occasions where you can already the benefit of feature learning already allows you to outperform the initial model, the initial random feature, and also possibly the kernel lower bound. So if we actually want to show that you can learn after one gradient step, you can learn a wide range of target functions with different sigma star, the better approach to do here would be actually to add random bias units. So by that I mean, our neural network does not have bias unit, but if you add bias unit but do not train them, then you can use a universal approximation property of the activation function to show that you can learn a much wider class of sigma star here. So this has been done in recent works by Alex Damian and also Alberto Vietti. Okay, so I think I should conclude. It's essentially the two parts of analysis. One is we first show that in the early phase, the update that the weight matrix receive is very much rank 1, if you look at the operator norm. And this rank 1 component is going to give you alignment with the linear component of the target function. And we also have conjecture of how the conjugate kernel is going to change, but I did not go through that in details. And then based on this rank 1 property, we can also characterize how much the kernel improves in terms of the prediction risk. And so when the learning rate is not too large, we can do a precise analysis via the Gaussian equivalence. And now we can show that the prediction risk always improve, but then it also cannot improve too much in the sense that it's going to be lower bounded by this dashed line. But we also show that when the learning rate goes to infinity in this regime, then you can exactly match this lower bound. Whereas if you take a very large step, that so here we can only analyze one gradient step, and in this regime we can show that if you choose a very specific teacher model, then after one gradient step, you can actually outperform this kernel lower bound. And there are quite a few open problems here. I'll just mention one of them, which is that right now our precise analysis really relies on the Gaussian equivalence, which is a bit underwhelming because that means that our model is it's basically linear. So it'd be very interesting to see like when does the Gaussian equivalence property actually fails, and can we actually still do the precise analysis beyond having this Gaussian equivalence. Okay, I think I'll stop here. Thanks. So I'll be happy to answer like more questions.
Thanks, Danny. I think one of our audience have